Hello, everyone. So I'll be going over chapter 7, which is a new concept of work and energy. So we are moving away from the Newtonian forces, and we are going to be then looking at this new concept, which is, called energy. So we're going to kind of talk about what energy is, what type of energies we have. Um, then there, some very important, for our particular chapter, energies like kinetic energy and potential energy that we're going to go into greater detail. Then talk about work as a physics concept and how it's related to energy, and basically cover very important concept in all of science, energy conservation, and some of the relationship of energy conservation to different type of energies and work done in the system. So let's kind of talk about, yes, right, in previous chapters, right? So we studied motion. And remember, we started with kinematics, which is study of motion and how the object is moving. And then we talked about Newtonian dynamics and why the object is moving. So basically, forces acting on the object make it move in a specific direction with a specific acceleration, and we could use that information, right, to find the speed, displacement, time, acceleration, some particular force of interest and things like that. So a lot of things we could do with that. So but still, the problem with that was the force, acceleration, velocity, displacement. All of those quantities are vectors. And it's never easy to work with vectors, as you probably have learned from this past 6 chapters. You always need to take into account their magnitude, their direction, and if they're two-dimensional, you have to, find the components. And if they're, let's say, multiple forces, you have to find, the net force or net velocity and things like that, right? So you have to break them down into components, add horizontals separately from the vertical components, and so on and so forth. So relatively complicated to deal with, vectors, and especially if you have multiple vectors in the system. So one thing then we get from this chapter is energy is some kind of scalar quantity uh, that allows us to calculate at least some of these things, like speed, a displacement, um, even the force, right? Some of those quantities without really going into those sort of like, let's say, analysis of Newtonian dynamics and things like that. That means we can find or solve similar problems that we used before, vector, let's say, um, calculations. So we can kind of solve same problem, but using the energy approach. And you can get the same answer at the end. In some cases, using the energy approach makes our calculation much simpler, because one of the things we can do here is we can then remember, if you're working with energy, we're working with some kind of scalar quantity, and it's not directional. So it's easy to generally work with scalar quantities. But even in this type of, let's say, some of the problems that we did before, right, even though we're dealing with still forces and velocities and things like that, but we can use energy approach to find some of the magnitude. So instead of velocity, we can find the speed. Instead of displacement, we can find the distance traveled and things like that. And we're going to learn all that in this chapter, because for many cases, energy approach is much preferred, because we can solve some of these complicated Newtonian problems with only in just few steps, and basically get some of the same results at the end. All right. So that's kind of what we're going to talk about in this chapter. So we'll talk about, well, let's say, this new concept of energy, which is generally not an easy thing to explain, because you can't necessarily see energy, right? So you can calculate some kind of energy of very specific type of, let's say, motion or display, or let's say position change and things like that. But it's not something that you can see, okay, or here's the energy or anything like that. So it's a quantity that we can calculate. And the energy is some kind of quantity, scalar quantity that can be associated with different things. So let's say there's energy associated with motion, energy associated with changing shape, changing height, and there's electric energy, there's chemical energy, and so on and so forth. So we're going to see different type of energy, let's say types. And one thing we have here is technically the entire universe can be described in terms of energy. So that's why this energy is a fundamental concept of science, not just necessarily physics. So that's why we're going to be looking at some of the type of energies, how to calculate those type of energies, and then we're going to learn how to put everything together. All right. So let's start with one very important thing about energy. Generally, we need to define always our system, just like with the Newtonian physics, remember, or the Newtonian dynamics. We need to define our object of interest and then all the forces acting on it and things like that. Here we need to kind of do similar thing. So we need to define a system. So the system can be just a single object. So for example, right? So I can think of like, okay, so there's a box and I have, a box as my object, right? So then I want to look at what happens to the box, and so on and so forth. Or I can say, okay, so the box is on the surface. So now basically what I have here is I have a surface and a box. But so far, one thing I can do is if I'm talking about just a box, I can say, okay, so here's a box initially at point A, and then maybe the box goes to point B, going from some point to another, point 1 to point 2, or point A to point B. That means what I can do here is I can look at what happens to my box. And then I can look at in terms of what is the energy of the box at point A compared to the energy of the box at point B. And then I can do a lot of interesting calculation from that, let's say, information. Now, I can also then take, for example, box and the surface together. I can say that my system is not just a box, box and the surface. All right. Or maybe I can say, okay, so it's not just box and the surface, maybe box, surface, and let's say the earth, right? And that means I have box, surface, earth, and then I can take, even more. I can go on, and then you kind of make my system more complicated and more complicated. So that's why technically, the system is important to define first. But once you define your system, then you are looking at, energy within your system. So the system, again, can be just a single particle, you can say, right? So it can be just a single particle, or it can be a collection of particles. Let's say it's either the box, just a single particle, or box and the surface, or box and the surface and earth, right? And things like that. Or it can be a region of space. I can say, let's say this room is a system, and I can look at in terms of what happens in the air molecules inside the room, right? Or I can take, the solar system as my, a system and things like that. One thing I can also do here, I can have my system vary with, with time, vary with time in size and shape. I can maybe have a spring, and if that's my system, well, I can compress the spring or I can expand the spring, right? I'm changing its shape as a function of time. So there are a number of, things I can do with that. But again, so most of the time, our system going to be maybe like a single particle. And then one of the things I can do here is this, right? So for example, here's, position A, here's position B, going from position A to position B, I can look at, the energy of the box at point A compared to the energy of the box at point B. And then I can conclude some interesting things from that, which we'll see in next few slides. All right, so one very important concept we're going to see is the conservation of energy. Because one of the things we have here is, for example, when I consider object at point A, so here's box at point A, and maybe this object going up an incline or something like that, and it goes to some point B over here. Okay, some incline to some angle theta. So some of the things I can do here is I can look at energy of the box at point A, and then look at energy of the box at point B. And under the right conditions, which we're going to talk about in a bit, under the right condition, energy of the box at point A can actually be exactly the same as the energy of the box at point B. So how can that be? Energy is the same. Well, because energy can depend on a number of things. So it can depend on energy of motion, energy of changing position, energy of changing shape, and things like that. And then when you're looking at energy at point A, energy at point B, you are looking at individual sum of different type of energies at some point A compared to the energy sum of the different type of energies at some point B, and then comparing the sum at point A and B. Things can change, but maybe their sum is exactly the same. All right, we'll come back and solve problems on this concept, but the idea here is that under the right conditions, energy of the object at two different points can exactly be the same. So then we can say that energy is conserved. Conserved means that it's constant, did not change. Right. So one very important type of energy, which is probably the simplest type of energy that we can consider, is energy of motion, which is simple enough because, if object is moving, it has this kinetic energy. If it's not moving, it doesn't have this kinetic energy. And then you can see that the equation for kinetic energy is 1/2 times mass of the object times speed of the object squared. So 1/2 mass times speed squared, right? So here we're using speed rather than velocity because technically it doesn't matter, let's say, in which direction you're moving, you're gonna have same kinetic energy because we're squaring that value, right? So we are pretty much looking at some kind of scalar quantity, and the units for the energy and kinetic energy and all of the different type of energy is actually joules. And you can see right from here, if you compare the units for the kinetic energy is mass in kilograms times speed square, and speed has a unit of meter per second, so it's kilograms times meter squared times over second square. So you can see, right? So this is technically the units for kinetic energy, but we define that to be joules. All right, so we'll use another, unit for the, or another, definition for joules in a little bit, but you can see, right, in terms of fundamental units of length, mass, and time, the joules is kilograms times meter square per second square. All right, so that's units for energy, any type of energy. And right now we're strictly talking about kinetic energy, which is the equation, right? You can see, right, 1/2 mass times speed square. Again, it is, in terms of energy of motion. And then you can see, right, if you're at rest, your speed is 0, so it's kinetic energy. So that's why the kinetic energy is the simplest one because it's, technically depend on your motion. All right, so here's kind of like some breakdown. You can see, right, energy on Earth originates from the sun, right? So we can see, right, energy on Earth is stored thermally and chemically. And the way, you have energy originating from the sun is that, the sun produces, energy, right, and radiates that energy. So whenever you see the sunlight is nothing but pure energy coming from the sun. And, Earth and all the, plants and us and everything, right? So basically receives that, a sunlight, and the sunlight is then absorbed. It's absorbed by our body, right? Our skin absorbs that, sunlight. The plants absorb the sunlight, right? And things like that. So, and it's, we can store that energy. So you can store in your body that energy. The plants can store, the Earth can store that energy. And you can see, right, the, energy on Earth is stored thermally and chemically, okay? So then chemical energy is another type of energy. We're not going to be looking at chemical energy, but maybe in your chemistry classes you'll be considering this type of energy. But for us, one thing we can have here is very energy is that we can easily convert energy from one type to another. So let's say if you have a light energy or heat energy, we can convert it to different type of energy. Heat energy is very difficult technically to convert, but it's still something you can do. Chemical energy, chemical energy can be easily converted to different type of energies, motion energy, potential energy, and things like that. And you can see, right, chemical energy is released by metabolism, and energy is stored as potential energy in objects' height and mass, and also through elastic deformation. So you can see here is kind of like a picture of different type of conversion of the energy. So you have nuclear energy in the sun's core. It's a nuclear energy because the subatomic particles inside the core, they smash into each other, and then they basically go from taking hydrogen and fusing into helium. That's how sun generates energy. During that process, energy is released, and it's a nuclear energy. and that nuclear energy becomes energy of the sun's hot gas, right? So basically becomes energy of sun's hot gas, and then and that becomes, energy of sunlight. Then that sunlight is, through vacuum, right, through space, moves toward us, and then it reaches Earth. You can see, right, that sunlight basically can be converted by plants to the chemical energy of grains and other foods. So it's, the plants absorb that energy and store it as chemical energy. That means they convert, the nuclear or light energy into a chemical energy. And then when you eat that food, right, then that food basically absorbed by your body and it's stored, right? So then that chemical energy can be converted to, let's say, kinetic energy. So that's why you need to eat food in order to be able to move around and things like that. You need energy, right? So that's why you have those energy bars and things like that. They're just, food with a lot of chemical energy that you can be released and allow you to, move around and things like that. So basically, if you don't eat for a couple of days, you can see that you don't have energy to, to be able to do, all the physical activities. All right, so we also have a potential energy, which is energy of a system determined by configuration of the system. So let's say if you have an object vertical height or object shape and size can be considered as a configuration of the system, right? So then in a way, if you have you can see, right, consider a book lifted up from the surface of table. So you can see, right, if you lift the book up, you are changing its height. And the potential energy is, or one type of potential energy is called gravitational potential energy, depends on the height of the object. And the reason it depends on the height of the object is because, like the name can suggest, gravitational potential energy. If you're changing your height, you're basically either going against the gravitational force or with the gravitational force. And, in that case, there is a stored potential energy. And potential energy generally is a stored energy that you can, let's say, store that energy and then be able to use that for other things. And one of the things we're going to see here is a lot of times that potential energy can be converted into motion energy. Let's say when you store energy, then you can use that energy to move. All right, so you can see, right, so you have a table. So for example, so here's a table. And then let's say you have a book. Okay, so let's say if I take then, surface of the table to be y equals 0, then you can see, right, if you lift the book to some, height h with respect to the surface of the table, right, which is y equals 0, right? A lot of times we call this y equals 0 as a reference position. So if you move that with respect to your reference position, then you can say that you're changing the height. So if you're changing the height, then there is a potential energy, okay? Again, the surface, right, y equals 0, it is then can be called a reference. So that's our reference position. And then every time there's a change in vertical position, that means there's some kind of delta y, right? You can see h equals some kind of delta y, change in vertical position. That means you are storing some kind of potential energy. That means you're storing potential energy when you're increasing the height, or you removing potential energy when you're decreasing the height. Generally it's kind of, the way to go. And we're gonna, again, talk about this in a little bit. Because things like this. So the book, when it was sitting on the table, its speed was 0. So then let's say when you move this to some height h and holding this, so it's still at rest, right? But let's say, again, let's say this is a reference position, y equals 0. And let's say here's the book. So you can see, right, book is some height h above the ground or the table. And if you're holding that, so right now it has no speed, okay? But as soon as, but what you have, because the book has a height with respect to the reference position, it has a kinetic, it has a potential energy. There's a stored potential energy because of that, change in vertical position. Because here's what happens after that. Imagine that you're holding the book and now you release the book. Well, the book not going to just stay there, right? It's going to start falling. Why can the book now fall? Well, because you had a stored potential energy, and that potential energy is now used to give the book Kinetic Energy. All that energy that was stored when it was sitting at this, initial, non-zero position, right? Now is, that position is decreasing, right? As you move toward the, this reference position, it starts moving faster and faster, because what happens here is that all that stored energy now is converted to kinetic energy. Again, we'll talk about that, but let's look at, in terms of this diagram. So this also, shows how we can take the, let's say, potential energy or kinetic energy and be able to convert from one type to another. Okay, so that's one of the important things that we can have. So generally, you saw already the notation for kinetic energy, and we use that as K. Okay, so remember, K is the kinetic energy, and it is 1/2 mass times speed squared. All right, so this is the kinetic energy. Now, one thing I can also show you here is the notation for the potential energy. And again, so what you have here is, actually, let me do this. So here's energy, and we usually represent energy with E. So this is like, let's say, energy of the system. So then energy of the system can be, at least for our, our particular chapter, right? We are looking at more or less two types of energies. So there is kinetic energy, okay, and there is potential energy. Kinetic energy and the potential energy. Well, the kinetic energy is one type, and here's the equation for that, 1/2 mv squared. Well, there are actually many different type of potential energies. There's a, potential energy due to height, potential energy due to shape, size, and things like that. So, two things that we're going to consider in this particular chapter are two types of potential energies. One type is gravitational potential energy. So gravitational potential energy, let me kind of do it like that. The other one is elastic potential energy. So elastic potential energy. Okay, so you have gravitational potential energy, elastic potential energy. So gravitational potential energy due to change in height, right? So this is basically every time there's a delta y, which is change in vertical position. And elastic potential energy is every time there's a elastic object that has been moved from equilibrium. So it can be like, let's say, basically anything that you can use to change shape, right? So for example, U is given to the potential energy. Capital U is what we use for the potential energy. So here's the equation for the gravitational potential energy. So it's mgy. That's the equation for the gravitational potential energy. So mass times gravitational acceleration times vertical position. You can see, right? So to make sure that we know that this is a gravitational potential energy, we use a subscript G. So gravitational potential energy is equals to mg times vertical position. All right. So then here's then elastic potential energy, which we're going to see again in a bit later on. So it's then 1/2 K, which was a spring constant, if you remember, or elastic constant, then times some kind of, and here I want to just use not X or Y, but maybe, S, because this is just a general displacement from the equilibrium position squared. That means, you basically have three equations, right? So, and those are kinetic energy, gravitational potential energy, and elastic potential energy, okay? And one of the interesting things about those three types of energies, right, is that you can easily convert one type of energy to another. And you can convert 100% of kinetic energy to 100% of potential energy. So let's say you started with 100 joules of, let's say, kinetic energy, you can easily convert that to 100 joules potential energy, either gravitational or elastic. So that's kind of, how we can, get this conservation of energy. Conservation of energy occurs because those type of energies easily can be converted from one type to another. All right, so let's see then what we have. And one of the interesting things about this energy approach is you always consider 2 points of interest, right? So, or you can think of like, let's say what we call like before and after, or, you know, initial or final, or point A to point B, or point 1 to point 2, so something like that. So here's, for example, this is going to be before release, okay? So that means you have before release, and then here you have then after release, okay? So generally that's kind of one thing we have with the energy, before and after, okay? So sometimes, you know, your motion, if let's say if it's a little more complicated, you can break it down into like different parts. Let's say that's why I like to generally use, instead of before and after, I like to use A, B, right? Or, you know, because if it's a little more complicated, then I can have A, B, C. So going from A to B, then going from B to C, and so on and so forth. So that's kind of like, you know, one of the things I can have. But for example, in this particular, so let me kind of, remember, you can always go back and see this diagram again. But what I'm going to do here is this. So I'm going to look at in terms of what I have for this particular example with this a sling. So basically we have before release, you have a stretched sling. So think like this, the sling itself has a rubber band, right? So, and it's an elastic object. So what you do here is you take the object, some piece of rock, right? And put it in a sling, and then you basically stretch it. Now, when you stretch it, you're changing the shape of the, you know, sling, right? Well, when you change this, you know, the shape, you store potential energy, and it's elastic potential energy, right? So let's use this as, you know, one of the things I'm going to do. I'm going to say that this is point A. Point A is when you take the sling and you stretch it and you're holding this. So that's before release, right? You're holding that. So then one thing I can say is I can say, okay, so here's my energy at point A. And energy at point A is generally then is sum of all the different type of energies you can have at point A. Well, right now I can look at kinetic energy at point A, then add this to the gravitational potential at point A, then add this to, let's say, the, you know, elastic potential at point A. So I can have something like this, right? And then what I can have here is then we release. So for example, when we release, we have several points of interest I can look at. First, maybe I can look at when, see this rubber band, when you release, it then pushes the rock to this position, right? So then what I can do, I can say, okay, so here's my position B, and then the rock gonna be moving, it's gonna be given some kind of initial velocity at point B, and then it's gonna move then slow down because of gravity, right? Slow down and stop at, let's say, this point C. Okay, so I have technically 2 points of interest, point A, point B, point C. Then I can say, okay, so here's my energy at point B, which is again now kinetic energy at point B plus gravitational potential at point B plus then elastic potential at point B. Then I can look at, okay, so then there's also energy at point C, which is then again kinetic, and you can see, right? So when I'm looking at energy at any particular point, I can represent energy, total energy, as a sum of those 3 types of energies of, you know, that we're considering. So gravitational at C plus elastic at C. So I have those 3 types of energies. And then I can compare them. I can say, okay, so here's energy at point B compared to energy at point A compared to energy at point C. And one of the things we can see in a little bit is that this is one of those situations where energy will be conserved. When energy is conserved, it means energy, total energy, at any point of interest during the motion of the object, let's say point A, at point B, at point C, it will be exactly the same. Remember, I'm not saying that kinetic energy will be exactly the same everywhere, or potential energy will be exactly everywhere. What I'm saying here is that the sum of kinetic and those 2 types of potentials at point A will be equal to the sum of kinetic and potential at point B it will equal to the sum of kinetic and potential at point C. Some things can change, right? But the sum will be the same. For example, if you see at point A, right, when you take the rock, put it in that sling, in the rubber band, and you stretch it, you're still holding it at point A. So technically here at point A, there is no kinetic energy because you're holding it. So that means what I can do here is when I'm writing energy at point B, so I can say, well, let me do it like this. Maybe I can say A equals B equals C, just so it be in order. So then here's what I have. So it's kinetic energy at A plus gravitational potential at A plus elastic at A. Their sum is equals to kinetic at B plus gravitational at B plus elastic at B. Well, that sum will also be equals to kinetic at C plus gravitational at C plus elastic at C. All right. So that sum of three types of energies at point A equals sum of three types of energies at point B equals sum of three types of energies at point C. Doesn't mean that, let's say, for any of the particular points you will have all those energies. It depends on a number of things. For example, since this is basically in my motion, right? So you can say, right, this is A because this is where the sling was stretched. So technically this is my point A. Then this is my point B, my point C. Depending which one I choose to be the reference, vertical reference point, then I might have different position for the gravitational potential energy, right? So for example, I can choose point A to be my reference point. Then point B is higher than point A. So, and point C is again higher than point, A. That means as the object goes from A to B, there's an increase of gravitational potential energy. Going from B to C, again, there's an increase of gravitational potential energy. And that's one thing we can do. So let's say I take this point A to be YA, right, equals 0. Well, if YA equals 0, look at equation 2. In this equation 2, if Y is 0, that means the entire potential energy is 0. The gravitational potential energy is 0. And that's one of the things I can do. That means, you can see, right, if I'm then looking the total energy of the system at point A, then it has no gravitational potential energy because it's my reference point. There's no gravitational potential energy at the reference point because Y is equals to 0 and the gravitational potential energy depends on that vertical position Y. Well, at point A, I'm still holding it. Remember, you stretch it and you're holding it, which means there's also no kinetic energy. Well, that means my energy at point A, there's no kinetic, no gravitational potential, but obviously since you're changing the shape of the, rubber band, right? The sling has elastic potential energy. And this guy here is non-zero, okay? Then when you can see, right, when you go to point B, at point B, now there is a vertical position, non-zero, so gravitational potential energy is non-zero, and it is given some kind of energy is non-zero. But then you can see, right, when you go to this position B, rubber band gets to, is sent to its, let's say non-stretched position. So this guy here is 0 because it's no longer stretched or compressed. So there's no energy if let's say no elastic energy if elastic object is not stretched or compressed. Okay. And then when you go to point C, look at point C. Point C is where the rock, right, they're going to slow down until it stops with the velocity of 0. Well, what you have over there is this. Well, it stops. It means that has no kinetic energy. That means this guy here is 0. Well, there's a YC, which is not 0. That means gravitational potential energy is not 0 because you are increasing the height. So you were increasing gravitational potential energy. But point C doesn't involve any elastic object, right? The rubber band stays there. So then this guy here is 0, all right? That means you can see from all of this when you're comparing point A. So here's point A. Well, point A end up only having elastic potential energy at point A. That means all of the energy is purely elastic potential energy at point A. Then when we go to point B, there is no elastic potential energy. because all of that elastic potential energy is converted to kinetic energy. Sorry, at point B. So kinetic energy and gravitational potential energy. That means one type of energy converted to two different type of energies. But when you go to then point C, you can see, right, you continue increasing your potential energy, but your kinetic energy then goes to zero. So then all of the energy is converted to the gravitational at point C. All right, so that's kind of what you have. For example, if we started with 100 joules of energy, then imagine maybe that's 100 joules of elastic potential energy at point A. When we go to point B, all that elastic potential energy is now converted to the kinetic and gravitational potential energy. And maybe one of the things we can have here is maybe like, let's say this guy here is 60 joules, and this one is, let's say, 40 joules. Okay? So that means 60 joules kinetic, 40 joules gravitational potential. You can see, right, their sum is still 100. But when we go to point C, there is no elastic potential energy, there is no kinetic potential energy, and only gravitational potential energy. That means all of the energy, all 100 joules of energy now is gravitational potential energy. All right. That means we went from, elastic to gravitational and kinetic, and then to fully gravitational. You can see, right? We converted energies back and forth several times, right? So this is kind of what happens. And when it's going from C back to B, basically converts back gravitational to, kinetic and things like that, right? So you can think like when it goes from C to A, it converts back everything, into the kinetic energy and things like that, okay? So those are the things we're going to be looking at, but this is kind of like the rough idea where we can see the transformation of the one type of energy to another type of energy, and how under the right condition, and as I said, right, so right now this is the right condition where energy is conserved. That means we have all those points, right, or any point, during this motion of the rod with the same total energy, and that is a very powerful tool that we can use. All right, so the condition of conservation of energy can slightly change if you consider, let's say, other things like friction and air resistance and things like that. Because when you have those things, then you can have some of the energy last in the system. That means, when you have 100 joules of energy at point A, by the time maybe you go to point B, you have only 80 joules. Well, what happens to then that 20 joules? Well, maybe that 20 joules was lost to heat, all right? And heat is type of energy that you cannot bring back anymore. Once you lost energy to heat, you basically it's pretty much gone. Nothing you can do about that, right? So, so that's kind of, what we have in terms of, that the energy will be lost to heat, and we will see some examples of that as well, right? Now, here's the interesting concept that we're going to be looking at, which is the concept of work done. Okay, so let's say in terms of what is a work done, will be in terms of energy transfer into the system. Because for things like this, for example, here's a box sitting at the reference position y = 0. Well, it's a box at the reference position. It has no potential energy. So if you're looking at, okay, so here's the energy, and let's call this at point A, right? Here's the energy at point A. So kinetic energy, gravitational potential energy, and elastic potential energy, right? So elastic potential energy. Well, it's not moving, so there is no kinetic energy. It doesn't have a height difference with respect to reference point, right? It is at the reference point, so there is no gravitational potential energy. We're not changing its size or shape, so there is no elastic potential energy. So what is the energy at point A? Well, it's 0. There is no energy. All right, then what do we do with that? How do we then provide energy to the system? Well, we can transfer energy into the system. So that means we can, as an environment outside of the system, right, we can transfer energy into the system. And we're going to see that in general, there are two types of transfer mechanism that we can use. One is, in this chapter, we're going to learn about that, right, is doing work. Well, work, you can see, right, is not something that in physics, is not something that has the same meaning as what we use every day. So in physics, work done means that our ability to transfer energy into the system, or basically change the energy of the system in some way, or allow us convert the energy of the system another way, and things like that. So basically transfer of energy, that's what work done means, transfer of energy. So for example, then let's say here's object at point A, but I want object to go to point B, but it has no energy. Okay, so on its own it's not going to do that. Well, what do we do? Well, one thing we can do, we can push it, right? So imagine if I push it in this direction with some force F, then the box will start moving, right? And then what we'll do here is that we'll make it move from point A to point B while we're applying this force F. Okay, so that means we can push, apply force. And when we apply force, if there is a displacement, you can see, right, there's a displacement delta x as a, as a vector, right? Or delta r, let's call this delta r. So basically, if you push and there is a displacement, that means we are doing work, because those are the two requirements. If you're pushing, because here's the thing, imagine, look at, I don't know, try to like push a wall. So you're pushing a wall is not moving. Well, you are pushing, but there's no displacement, right? That means you are not doing any work, okay? The idea here is that when you push something, there has to be displacement, position change. And if there is a position change, then you can say, right, okay, then the work done, using capital W for that, is equals to the force magnitude times this displacement, okay? So in this picture, it shows that, so technically sometimes you can apply force at an angle theta. Then if that's the case, then one thing you can do, so imagine, right, so you can say this is the displacement vector, delta r, and this is the force vector, F, and this is then the theta, which is the angle between those two vectors, displacement vector and force vector. Then you find this angle theta between displacement vector and force vector and multiply F times delta R and cosine of theta, okay? So that's what we have. So you can see, right, this equation represents that. Magnitude of the force times magnitude of the displacement times cosine of angle between force and displacement vectors. All right, so work itself is a scalar quantity. You can see, right? So for example, if you take the box and you push it with some force of 10 newtons, and the box, so here's point A, here's point B, right? It goes from point A to point B, and let's say it undergoes displacement of 10 meters. Remember, 10 meters in terms of, let's say, x hat, right, in this direction. One thing I can do is I can calculate the work done, which is magnitude of the force, so just 10 newtons, magnitude of the displacement, so just 10 meters, and then times cosine of angle between them. Well, you can see force and displacement both, pointing in a positive x direction. Both are basically parallel in the same direction. So angle theta is 0 degrees. So it becomes 10 times 10 times cosine of 0. So this becomes 100 newtons times meters. That means we pushed this box with 10 Newton force, and this box moved from point A to point B, basically moved 10 meters. As it moves 10 meters, displacement of 10 meters, the work done by us, because we pushed, is 100 newtons times meters. So then what we do here is this 100 newtons times meter, the Newton times meter is a unit of energy, so we can replace that by 100 joules. That means you can see, right, joule is also Newton times meters, okay? So it has the same, it's the same unit, the equivalent. So, but obviously, remember Newton is meters, it's mass times acceleration, right? So it's kilograms times meters per second, second square. So this is just the newtons. Remember, so if you do newtons times meters, becomes kilograms meters square per second square. And that was the first thing I said, right? As a different definition of joules. So you can see, right, they're kind of equivalent. So newtons times meters or kilogram times meters square per second square, both give you joules. Right. So this is kind of like a simple example of that. And obviously for, if you have a force at an angle, right? So here's some kind of angle theta. You can also, go back and use this, whatever theta it is. So let's say 30 degree or whatever it is, right? So then you can use that. Obviously you're going to get a different value, right? But the idea here is you are using magnitude of the force times magnitude of the displacement, and then getting the cosine of the angle between. So you can see, right, the theta is between displacement and the force. So work done as a scalar quantity can be positive, like in this case, right? So if I do this, so cosine of 30, what was cosine of 30? Right, it's 0.866, then times 10, times 10. So what I get here is this, 87 joules, roughly, right? So I get 87 joules. So you can see, right, if I pull or push at an angle, I'm actually transferring less energy, because it's, what I have here is this force has only, X component, basically the parallel component to the displacement actually doing work, where perpendicular component of this force is actually not doing work. And which, we're going to see in a minute that any force that is perpendicular to displacement is technically not doing work, including a component of a force. So, but technically, it can also be negative. So when is it negative? Well, think like this. While you are pushing this force by 10 newtons at 30 degrees above the horizontal, maybe then there's another force here, could be friction, right? That acting at, let's say, 5 newtons. So acting, against, let's say the box, right? You're pushing, it's sliding, but there's a friction, 5 newtons in the negative x direction. Let's say like that. So what is then, so then this will be work done by this applied force. So what will be then the work done by the friction? Well, the friction applies 5 newtons of force. So we write down its magnitude. Well, the box still moves 10 meters to the right. So it's 10 meters, its magnitude. And then this is cosine of theta. Well, the theta for this work done by this force is the force direction relative to the displacement direction. And you can see, right, displacement direction is here, force is there. So the angle between them is 180 degrees, right? Because force is to the right, sorry. The displacement is to the right, force of friction to the left, right? That's a kinetic friction. That means what I have here is cosine of 180 tells you that 180 is the angle between displacement and this kinetic friction, which cosine of 180, if you remember, is -1. So then 5 times 10 times -1 gives you -50 joules. Okay. All right, so now we have two things. We have one force that we calculated and does 87 joules of work, positive. Then we have another force that is doing work as the box moves from A to B, but it's doing negative work. And so what does it mean, positive work or negative work? Well, it means if the force doing positive work, so you can see, right, work done is positive, that means this force transfers energy into the system. So that means, for example, right, you can see, right, work done by this force is positive, so energy goes into the system, okay? That means plus 87 joules, added to the system, okay? So added to the system. Well, work done by kinetic friction is less than 0, which is -50 joules. Well, if the work done is negative, it means it's removed from the system. Removed from the system. So now what we have here is we can then calculate the net, where you have two forces, right? Applied force and friction force, both transferring energy into the system or out of the system, but net effect will be, they're pretty much algebraic sum. So it will be, because they're scalars, remember. So what you do here is 87 minus 50, and then the net here is, what is it, 23 joules? That means you have a net of the, that no, it's like 37. What am I doing here? So 37. Okay. So 37 joules. All right. So 37 joules total transfer into the system. Why? Because this 37 is positive. Okay. So that's kind of, what we have in terms of this. Positive work done means energy transferred into the system. All right. So again, here's the in terms of if you are pushing in the direction of the force, and force is at an angle, right? You can see that in terms of force has two components perpendicular to the displacement. You can see, right, displacement is in a positive x direction. So this component is perpendicular to the displacement. The other one is parallel to the displacement, okay? And one thing you will see here is the one that is perpendicular. So you can see, right? So if I do work done is equals to by perpendicular component times this displacement times cosine of the angle between displacement and the perpendicular component. You can see, right, perpendicular component to the displacement has an angle of 90 degrees because it's perpendicular to displacement. Well, what is cosine of 90? That's 0. Where this guy, parallel component, well, there is in the same direction, so angle theta is 0 for that, so it does a positive work. So it means, this is done by the parallel component, this is done by the perpendicular component. And one of the things we see that every time the force is perpendicular to the displacement, that particular force never does any work. All right. So here's few examples of, let's say, what will happen or under which condition the work done is positive and under which condition the work done is 0, and under which condition the work done is then negative. So imagine you have a box initial, so this is before. So this is the box that is moving initially to the right. And then what we do here is we apply force. This red is the force in terms of its magnitude and direction. We're going to assume that it's a constant force the entire time. But, imagine then when you apply that force, look at the displacement. So here's the displacement. In this case, you can see, right, force is to the right, displacement is to the right. That means angle theta is 0 degree between them. And then when you do work done is equals to F times displacement. So FD cosine of 0 degree, you basically get FD because cosine of theta here is, or in cosine of 0 degrees equals to 1. So in a way you can think of like this is the maximum, right? Positive work done. When you apply force in the direction of displacement, you transfer maximum amount of force, maximum amount of energy. Well, what happens if your theta is less than 90 degrees? So basically you can see, right, it's greater than 0, but less than 90. Well, in that case, you're still doing positive work done because try to plug in cosine of 60, 70, 30, 20, you're going to get a positive number, like 85, right? So you're going to get a positive number. But, closer that theta here is to 90 degrees, technically smaller the effect of the force on, amount of work done, right? But it's still positive as long as this condition is satisfied. Remember, the work done uses magnitude of displacement and magnitude of the force. So FD always positive quantities. The only way it can be negative if the cosine of theta is negative. All right, so, and here's one other thing. Let's say if the box is moving to the right, and this is the displacement, right? But there's a force acting on it which has 90 degree relative to the displacement, which means it's perpendicular to displacement. Well, remember the equation, work done equals force times distance times cosine of angle. Well, in this case, force, displacement have, angle relative to one another, which is 90 degree. Cosine of 90 gives you 0. That means any perpendicular to displacement force does 0 work. All right. So this is the condition where the work done is 0. Force has to be perpendicular to displacement. Every time that's the case, it doesn't do any work. That means it doesn't transfer energy into the system or doesn't remove energy from the system. All right, so imagine then again, so another case where the box is still moving to the right, okay, still moving to the right. But what happens here, there's a force acting in this direction. Well, you can see right now, if you take the angle, right, angle here is greater than 90 degrees. Well, let's say it's, I don't know, 120. Well, if you go in here, plug in 120 over there, well, you're going to get a negative number. Cosine of 120 gives you a negative number. Cosine of 100 give you a negative number. Cosine of 150 give you a negative number. That means work done is going to be negative, which means that this particular force, in this case, removes energy if it's acting like that. That means if you're pulling moving object, right, if you're pulling in opposite direction, remember what's going to happen? Look at the velocity vector here and the velocity here, or the magnitude, right, in terms of, you're going to make it slow down. It's going to, slow down. Here, if I kind of go back to the previous slide, you can see, right, when you do positive work, so when you do positive work, in both cases here, we do positive work, look at the speed here compared to speed over there. Speed is increased. Speed here compared to speed over there. Speed is increased. That means one thing that we get out of this is when you do positive work, object moves faster. When you do zero work, object has the same speed before and after. But when you do negative work, look at it, object slows down. Because things like this, you remove energy, it has no more energy or less energy to move, so it moves slower. And then obviously, here's a case where you are, pulling the box as it's moving. So things like this, box is moving to the right, you're pulling to the left, angle is 180 degrees between them. That means cosine of theta is -1 because cosine of 180 is -1. And then you're doing maximum amount of, or removing maximum amount of energy. So you have negative work done, which means there's a removal of energy from the system. And obviously you can see that what happens, well, it slows down. Speed is less compared to, before and after. All right, so let's see in terms of a force condition, right? So there's no work done if the object undergoes no displacement, right? So as I said, right, if you try to push the wall if not moving, you're not doing any work. If you lift the object from the ground, there, you are technically doing work because you are, changing its position. But if once you lift it and you're holding it, if you hold it for like few seconds, during that few seconds, as long as you're not lifting upward or downward, if you're just holding it, you're not doing any work because the object has no displacement. So you're not really doing any work. You can see then that's basically the most important thing. Another one is the force is perpendicular to displacement. That means, for example, if you have an object goes from point A to point B, see, during the motion, this object has a normal force acting on it, and it has a gravitational force acting on it. So since gravitational force is W, sometimes we use W for that. Starting in this chapter, I'm going to use F of G for the gravitational force because I'm going to use W for work done. All right, so normal force up, gravitational force down. Well, here's a displacement vector. You can see, right, displacement vector is horizontal. So the normal force and gravity in this case are perpendicular to the displacement. So technically work done by normal force is 0 and work done by gravitational force in this case 0 because both of those are perpendicular to displacement. Doesn't mean that they're always the case, especially for the gravitational force, but it's always the case for normal force. Normal force never does any work because no matter how the object is moving, normal force is always going to be perpendicular to motion, which means that it will never contribute to the amount of energy added or removed. Okay. So here's one other condition which usually we're not really looking into that. It says part of the object on which the forces act undergo no displacement, even if the other object or the other parts of the object do move. So we usually don't look at something like that. For us, we're dealing with some kind of object that all the parts moving together, sort of. All right, so here's like a simple example that we can, look at. A man cleaning a floor pulls a vacuum cleaner with a force of magnitude F equals 50 newtons at an angle of 30 degrees with the horizontal. Calculate the work done by the force on the vacuum cleaner as the vacuum cleaner is displaced 3 meters to the right. All right, so we're looking at that in terms of work done by this. All right, so what I have here is I'm given the force, I'm given the angle with the horizontal, and you can see, right? So if I'm doing the free body diagram, here's the object, which is a vacuum cleaner. So I'm going to put in a coordinate system like that. So, so let me kind of do it like this, right? And this is my displacement delta x, because it's horizontal displacement. And what I have here, I have three forces. So I have normal force, I have weight, and I have the applied force. Then technically what I can do here is say, all right, so here's the work done by normal force. Here's the work done by the gravitational force. And here's the work done by this applied force. So this is my applied force. Well, normal force, here's its magnitude. Here's displacement. Then here's cosine of theta. But you can see, right, displacement is horizontal. Normal force is vertical. They're perpendicular. So it's equals to 0. That means, again, because displacement is horizontal and normal force is purely vertical, right? They are 90 degrees with respect to one another. So cosine of 90 gives you 0. Let's look at the gravitational force. Well, its magnitude is mg. Displacement is delta x. But then when I'm looking at the theta, here's the theta. Again, there's a 90-degree difference between them. So again, cosine of 90, and I get 0 there. So again, gravity and normal force not doing any work in this example. How about applied force? Well, it has a magnitude of 50 newtons. There's a displacement of 3 meters. And there's a cosine of 30 degrees. I plug in everything, and what I do here, I calculate positive 130 joules. What does it mean? It means if you push the, or pull the vacuum cleaner 3 meters by applying 50 newtons at an angle of 30 degrees, you transfer 130 joules. Because if I calculate the net, it will be work done by normal force plus work done by the gravitational force plus work done by this applied force, and I only get net of 130 joules. And since it's positive, that means system gained 130. Okay, because there's a positive work done on the system. All right, now what do we get in terms of that particular example? Okay, so let's say you did positive work, net positive work of 130 joules. What happens to the system? Well, what happens to the system here is, well, the system gonna be, gaining energy. Okay, so remember, if you consider that picture over there, right? So for example, see, you have this applied force over there, and let's say there was no friction, right? So one thing you could see here is there's applied force. Well, it has a horizontal component and it has a vertical component. But we know that this, this vacuum cleaner was moving to the right, right? It changed the position by 3 meters. At least, we considered that particular 3 meter of interest. All right, so look at this force. This is the X component of this applied force. Well, you have a horizontal force to the right, and there is nothing else to cancel it. Well, if you have now a force pushing the vacuum cleaner to the right, or the component of that, right? Well, it's it's going to speed up, right? It's going to make an acceleration. There's acceleration due to this force, which means it's going to speed up. But again, what we're going to be doing here is we're not necessarily going to be looking at acceleration. We're not looking at acceleration at all in this chapter. We're looking at the force and effect of the force, which is change in motion. But we're going to look at change in motion in terms of speeding up or slowing down type of thing. And obviously you can imagine, right? If the vacuum cleaner is sitting over there at point A, and then you apply this force, then it's going to start, speeding up to the position B, right? Because you have a force pushing it or pulling it from point A to point B. And that's kind of what we are looking at, but we are looking at it from the point of view of kinetic energy. So let's say I have a kinetic energy at point A and kinetic energy of point B. I want to look at, okay, what is the kinetic energy at A relative to kinetic energy at B? Because that's how I can figure out what happens to the object, right? Because here's what I have. So let's say here's a kinetic energy at A. If the vacuum cleaner is at rest at point A, That means there is no kinetic energy at point A, right? Because if it's not moving, it's just sitting there at point A to start with, it has no kinetic energy at point A. But then obviously it's then being pulled and it's moving to point B. Well, when it gets to point B, right, we're assuming it's still being pulled. We just stop, let's say our, let's say measurement at point B. Well, at point B, now it is moving with some speed because it's being pulled to the right. Now this is not zero, right? So then this is some positive quantity. By the way, kinetic energy itself can never be negative quantity because kinetic energy equals 1/2 times mass times speed squared. So it's always positive. But what we are interested in is what happens if you are looking at kinetic energy at A and B, comparing them. Because here's the thing, if I give you kinetic energy at point A, let's say, even if it's not zero, right? For example, so let's say this is 10 joules. Okay, so kinetic energy at 10 joules tells you one thing, that this object, let's say it's moving at point A because it has a kinetic energy there. Doesn't matter which direction it is moving. It is moving at point A because it has a kinetic energy. Now, if I then want to understand what happens to the object, I need to compare it to some other point. So let's say point B. So how do I know if object basically going to speed up or going to slow down when it goes to point B? Well, what I do, I look at changing kinetic energy. I compare them. Think like this. If I look at kinetic energy at point B and I get 20 joules, well, 20 joules is greater than 10 joules, which means as object goes from point A to point B, it gains kinetic energy. Well, when you gain kinetic energy, doesn't mean that, what it means is basically, you can say, right, here's the kinetic energy. 1/2 mass times speed squared. Well, when you gain kinetic energy, it doesn't go into changing the mass. What it does, it goes into changing your speed. So if you have more of it, you're going to be moving faster than before. That means when I look at the object at point A and at point B, by just looking at its kinetic energy at point A and B, I can see that it has more kinetic energy at point B. That means going from A to B, it is speeding up, right? It's moving faster. Now the question is why? Well, because it's being pushed, right? But one thing I want to look at here is from the energy point of view. Why is the object moving faster at point B compared to point A? Well, because as the object moving from A to B, there is a transfer of energy into the system. So the system is given energy. Well, if you're given energy, you're going to be moving faster than before because you are gaining energy. That's why positive 130 joules of energy means that you can use that energy to move faster. Okay. What happens, let's say, if you remove energy? Well, if you remove energy, then if you're going from point A to point B, maybe your kinetic energy is going to be 5 joules. Well, that's because if you remove energy, you're going to have less energy to work with. So you're going to slow down. So that's why one of the important things we can do here is, instead of looking at, let's say, acceleration and so on and so forth, all we want to look at here is this. When we do work, how does it affect the kinetic energy of the object? And this work energy theorem that we're going to look at here does exactly that. It says that when you do work, that work, total work done, always will go into changing the kinetic energy of the object. So this is called a work energy theorem. So that's why what we have here is, see, this is delta K, changing kinetic energy between any 2 points. And this is equal to directly of the total work done on the system. That's why if you don't do any work on the system, kinetic energy delta K is 0, which means K before and after is the same. That means you're moving the same speed, which makes sense, right? If nobody pushing or pulling, you continue moving the same speed. If work done total is positive, then delta K is positive. Well, delta K positive means, see over here, right? If this quantity to be positive, which is final minus initial, can only happen if final is greater than initial. So let's say 20 minus 10, and you get positive 10 joules, right? See, it's positive. If delta K is positive, you have greater kinetic energy, which means you're moving faster. Because if final kinetic energy is less, so let's say 10 minus 20, well, what you get here is negative 10. What is negative 10? Negative 10 delta K means you are, moving slower at final point, which means you are moving, you have less kinetic energy. Why do you have less kinetic energy? Well, because delta K is directly equals to work done. So if you have a negative work done, means that you remove the energy, well, you then means you have a less kinetic energy at point B, right? So you can see how they're related, right? So delta K is directly equal to the net work done. If the total work done is positive, you're moving faster. If the total work done is negative, you're moving slower. So that's kind of pretty much what we have. So that's why if, okay, so right, total work done is positive, which means delta K here is positive. Delta K positive means K final is greater than K initial. Well, if work done is, total work done here is negative, means delta K here is negative. Well, delta K can only be negative if K final is less than K initial, all right? So technically, what does it mean K final greater than K initial? Means V final greater than V initial, so you're moving faster. K final less than K initial means V final is less than V initial, so you're moving slower, okay? So in a way here you have speeding up. Here you have slow down. Okay, those are the conditions. And you can see, right, I'm not looking at any type of acceleration or anything like that. What I'm doing here is I'm looking amount of work done on the system, and I can figure out if I'm going to slow down or speed up just by looking at the kinetic energy or, or the work done on the system. All right, so here's one simple example. So we'll do this example now, where I have 145 gram baseball is thrown so that it acquires a speed of 25 meters per second. All right, so it seems like a kinematic problem, right? So you have a mass of the object and you have or even dynamic, right? So you take object of 145 gram and you throw it with 25 meters per second. Okay, here's the question, what is its kinetic energy? Well, to find the kinetic energy, if you remember, you take 1/2 times mass of the object times speed squared. Well, 1/2 mass is 145 grams. Well, we need to convert it to kilogram, 0.145 divided by 1,000, right? Then times 25 meter per second squared. We do this calculation, we will get 45 joules. That means the instant it's given 25 meter per second speed, its kinetic energy is 45 joules. All right, so it says, what was the net work done on the ball to make it reach this speed if it started from rest? All right, so how does it start from rest and how does it gain that energy? Well, you kind of have to look at, sort of what happens, right? So for example, I'm going to try to draw this. So let's say here's the baseball player, right? Well, what it does here, it takes the ball here, right? So this is his hand. So it takes the ball here, try to make a motion, right? So let's say you have a ball, your hand, you extend it back, and then you move your hand from back to front to release the ball, right? So it's basically moves this from here to there, and then it releases the ball. That means here, the ball moves from this position, right? When the head is in the back to the when the hand is in front. Just try to basically, throw, right? The throwing motion. Going from back to front, well, then there's a distance, right? It has to travel. And what you do here, you push it, right? You basically apply force. That means you are doing work. So you're doing work, you apply force, and it's moved this distance d. Well, that's the work done. Well, how much work did you do? Well, remember, work done is equals to changing kinetic energy. Well, if let's say this is point A when your hand is in the back, and this is B when your hand is in front, and then that's where you release the ball. So let's say it's KB minus KA, changing kinetic energy final minus initial. Then because it started from, we calculate, right? This is basically kinetic energy at B when it's released. So it's 45 joules minus kinetic energy at A, but it starts from rest. So it's 0 kinetic energy at point A. Well, work done is then equals to 45 joules. Because your changing kinetic energy is 45 joules, then it's also equals to the total work done, okay? Because assuming that there's also gravity, but gravity acting perpendicular to your displacement, right? So then you have all the work done due to the fact that you're pulling it forward. Okay. So here's one more example. All right, so you have a box, 6 kilogram, initially at rest, is pulled to the right along a frictionless horizontal surface by a constant horizontal force of 12 newtons. Find the block's speed after it has moved 3 meters. All right, so you can see here's the free body diagram. A block, you have 3 forces acting on it, and it's moving to the right, distance of 3 meters. So technically then, what I have here is, here's the net work, which is work done by normal force plus work done by gravitational force plus work done by applied force. Because I have those 3, so you can write frictionless means there is no friction, but I have normal force and I have gravity, and you know those forces, and you can like writing work done by each force, but then you can recognize directly, if you remember, right? We talked about, you can see that normal force is perpendicular. Remember, this is the displacement, right? Normal force is perpendicular, so it does no work. Gravity is perpendicular to displacement, so it does no work. That means the only work done is due to that, push force. All right, so then the net work is due to that push force, which is magnitude of push force times delta x times cosine of theta. Well, the force is 12 newtons, displacement is 3 meters, and force is in a positive x direction, just like the displacement, so theta is 0 degrees. All right, so then what you get is 12 times 3, right? So we get 26 newtons times meters, or just 26 joules. All right, I just did not calculate that correctly. My math is off. So 13 times 3 is 36. All right. 12 times 3 is 36. There you go. Oh my God. All right. So anyways, 36 joules. So positive 36 joules, which means we transfer 36 joules into the system. Well, what happens when you transfer positive 36 joules into the system? When you transfer into the system, well, it's going to speed up. Remember, initially it's at rest. That means initial velocity is 0. So what do you want to find here? What is the final velocity? Why is there going to be a final velocity? Because we transfer energy into the system. And according to this work kinetic energy theorem, if you have a non-zero positive work, well, it's going to then change your kinetic energy. So K final minus K initial. Well, remember, K final here is 1/2 mv final square. K initial here is 1/2 mv initial square. But because there is no initial velocity, this entire term is 0. That means net work done here is just 1/2 mv final square. And then what I have here is, I switch the sides, so it becomes 1/2 mv final square equals then work done, total work done. And what is that? Well, that's 36 joules. Then what I do from here, I can go ahead and calculate the speed, because that's what I want, right? This is what I want. Then final speed is equals to 2 times 36 joules divided by the mass, which is 6 kilograms. And because speed was squared, so we take the square root. All right. So I plug in everything, I calculate, and I get 3.5 meters per second. So that's the speed of the block when it gets to that final position. That means 3 meters with respect to its starting point. And you can see, right, it is moving faster because it picked up speed. Okay.